All right, let's get started. Kernel 1 is due this Thursday. Hello, let's get started, okay? All right, and as usual, if you have code from previous semester, please don't copy from it. I know, when it gets closer to the deadline, people become more desperate, and so make sure your partners are not doing that. Hello, please, if you want to talk, please talk outside, okay? All right. And again, the reminder is to go through everything in the grading guidelines to make sure that you follow the grading guidelines. And if you are still confused about the grading guidelines, please come talk to me during office hours or, send an email to me. And make sure you verify your kernel submission, get a pristine, kernel code from the spec, and then apply, what you submitted on top of that, and make sure everything is working as you expected, okay? And also try to coordinate your team so that only one person makes submission. You don't want multiple people make submissions and they all get confused and things like that. All right. Yesterday somebody asked me a question about the midterm, and I updated the class webpage about the midterm information. So midterm exam is next Monday during class time, so it's going to be take up the entire class. So, an hour and 15 minutes, although the exam was really designed for like 80 minutes or something like that, so there should be plenty of time to finish the exam. So during class, the location is going to be SGM 101. So SGM is the, I guess, yeah, in the class webpage, there's a map of where SGM is. The coverage is... So the coverage is chapter 1, 2, 3, 4, but only the stuff that are covered in lectures that you're responsible for. Anything any part of the textbook that we're not covering during the lectures, you are not responsible for them. Okay. So so over here I listed as the following. From lecture 1 through today's lecture, because today we're still talking about chapter 1. We will finish chapter 1, and we're going to spend the rest of the lecture talking about chapter 6. Okay, so today's lecture is part of the midterm exam coverage. So from lecture 1 through today's lecture, minus anything that's in chapter 5 and 6. Okay, so the exam will not. So chapter 5, 6, they're all part of the final exam coverage, and the midterm we will not ask anything from 5 and 6. Okay. Please read, yesterday's item in the news section of the class webpage and follow the links to the course description webpage. Okay. So today, after I finish talking about chapter 1, I will, look at that, look at these web pages, and we'll briefly talk about, more about the midterm. All right. Okay. So let's, go ahead and try to finish chapter 1. All right. So. We'll continue with files because this is the stuff that you need to implement for your kernel 2 assignment. And kernel 2 assignment, starts, I guess this Friday. So hopefully, today you will have all the backgrounds that you need for implementing, VFS. Okay. All right. So last time, I guess we were talking about, opening files and, still, dealing with the file descriptor. So today we start by looking at how our files represented, so over here this is kind of an important slide. It tells you that on Unix everything has a path name. Okay, so it's almost everything. So the idea over here is that if you want to go to a device also has a path name. It's as if they're part of the file system. Okay, so the file system is the way to pretty much get to everything in the extended address space. Okay, including devices, storage, and other stuff. Okay, file directory, devices, and devices, they are represented as files. So I guess we sort of had a brief introduction on it, right? That if you look at a file and the file is a special file, that means that if you open up the file, you only see 2 numbers. One is the major, the major device number. The other one is the minor device number, and those are, the representation of a device, right? And then you use the major device number to select which device driver, and then when you need to interact with the device driver, you pass the minor device driver to that device driver and say, I want you to access, device number 3, under your control. Okay, so that's where, all these things sort of fits in. Okay, and over here, these are all, kind of devices, and they're all represented, using a path name. Okay, so, the major API for talking to any kind of a device or even directories are using open. When you try to get access to a particular device, you use the open system call, right? So, so Unix, in this way, it's very uniform. If you want to open a regular file, okay, you give it a path and you open it, okay? If you have a special file, you do the same thing. If you want to open a, over here, this is sort of a console device. Okay, it's a teletype, something you sit in front, and you can type and you interact with your system. You also do open, and in this case, it will return to you the same thing, a file descriptor number, and this file descriptor number will eventually point to the file. Okay, so remember, right, the file descriptor, so there's something called a system file table, right, system file table. Okay, and inside over here, there's an entry. The last entry points to an inode. It's an inode pointer, and that one points to, depends on whatever that is. If it's part of the file system, it will point to a file system implementation of that file. If it's a device, it will point to, somehow it will lead you to the device driver. Okay. All right, and to read data from a file, you use the read system call. To read data from a device, you can also, so over here is the device. If you want to read a few bytes from the device, you can also use the read, system call. Okay, so things are very, uniform. All right, and the directory is implemented as a file. So over here it says, a directory is a file. Okay, so when you want to open a directory, you can also just say open, use open to open it, to open that particular inode, okay, or to open that path that reference that particular inode, and then you can start reading data from it. Okay, but usually the directory, you don't really want to read the directory that way, so there are additional APIs that are provided so that you can actually read a directory. Okay, but in general, anything that, anything in the file system, as long as it looks like a file, well, you can open it, you can read it. Okay. All right. So the directory, it's a structured file. So if you want to interpret the data inside the directory structure, you will, you will use other APIs. Okay. So these are interpreted by the operating system as containing references to other files and directories. Okay. The way that directory works is that the directory contains references to other directory, we call them subdirectories, and also, it might be files. Okay, so this picture shows you an example of a Unix file system. Okay, it starts at the top, right? So the directory is organized into a hierarchy. Okay, and the way the references work, right? Over here, I highlight the word reference, is for a path name that maps to an inode number. Okay, because everything is represented as inodes. Okay, so the file is represented as an inode, so therefore a directory is also represented as an inode. Okay, so therefore inside the directory, all it has is a list of, subdirectory names or file names that are inside the directory, and then their corresponding inode number. All right, so it's just a simple list of, key value pairs that are stored in the directory. Okay, so over here, here's an example. Let's say that in the root directory, okay, you have these 5 entries in them. Okay, one is called Unix, the other one is called etc. The other one is of home, proc, and dev. Okay, each one of them will reference another inode, right? So here's a root inode. You open it up, and then you find out that there are other, there are these names followed by, their inode references. Okay, if you follow this guy, so this guy will take you to an inode, and this inode, when you open it, you say, oh, it's a file. Okay, so over here, we're going to use this notation on this picture where the orange stuff represent a file inode, and the blue stuff represent the directory inode. Okay, so this directory, it has 5 entries. Okay, so actually the way the directory is implemented, when you open stuff at this level, you see these 5 entries, so you know that this guy is a directory, but you have no idea what they are pointing to. Are they pointing to files? Are they pointing to directories? Are they pointing to devices? You don't really know. Okay, only when you follow the inode reference, at that point you will figure out what this is. Okay, So when you go to the root directory, you know that there's an entry called Unix, but you don't know if it's a file or a directory or device. You follow that pointer, and then when you open up the next level INO, you say, oh, it's a file. Okay, etc. You follow the pointer, and then this one, when you open it up, you say, oh, it's a directory, and therefore you have to interpret it as a directory. And again, it's a list of name followed by INO numbers. Okay, so in this example, there are two entries in here. One is called password, and the other one is called MOTD. If you follow this one, both of them will lead to files. And then the next one is the home directory. You're probably very familiar with Ubuntu. From home, they points to a particular user, and then it comes can be very, very deep into your home directory. Okay, and then the other ones are the same. Okay, so the directory maps a file name to an INO number. Okay, so this here has 5 entries. Each one of them is a file name and a directory name. They get mapped to an INO number. Okay, and an INO. So what is the idea of an INO, right? INO, the high-level concept is that it maps an INO number. Okay, so it's just a number. It mapped to sectors on disk. Okay, and again, this mapping is not a direct mapping. It might go over several levels of indirection, and eventually it maps to where the data is stored. Okay, if it's a file. Okay, if it's a directory, then again you come back right here. If it's a special file, it will point to the device driver, etc. All right. Okay, so here is a sort of a more detailed example of what a root directory entry might look like. Okay, so a root directory entry, right? So again, since it's a directory, okay, it's just a list of key value mapping, right? In this case, the key are the name of the components that are inside that directory, and then the values are the INO number. Okay, so the root directory might look just like this. Okay, it has 7 entries, right? In this picture, it has 5 stuff. It has 5 things in them. But in any kind of directory, there's actually 2 extra entries. One is called dot. The other one is called dot dot. Okay, so dot is the INO number. So this one maps to an INO number. That is this directory. Okay, so there's a self-reference in an INO. Okay, so say that what this directory INO, it contains a self-reference over here, and that entry's name is dot. Okay, and then there's another entry named dot dot. That means that it's the parent directory's INO number. Okay, so this one, if you look at this one says, the self-reference is equal to 1, and the parent is also equal to 1, which means that this is the root directory. Okay, so the root directory is the only one where the dot entry and the data entry are the same. Okay, the rest is because the directory is a hierarchy, so any directory is not going to have itself as the parent. All right. So when you implement, VFS, you got to make sure that that these kind of rules are followed, and there should be only one inode that have a self-reference, which is the same as the parent reference. Okay. All the other directories shouldn't look like this. All right. And then this guy has 5 entries, right? Unix, etc., home, proc, and dev. Okay. So again, just a table, map them to a different INO number. Unix is INO 117, etc. is INO 4. So again, the INO, you should think of them as a big array of nodes. Okay, so it's a data structure that's an array, and then this one name an index into that big array. Okay, so INO 177 is Unix, etc., and home, proc, and dev. All right. So this is just what a sort of directory look like. What does a file look like? Right, a file, I mean, you open a file in warm-up 1 and 2, right? I mean, the file, and also on Unix, when you do ls, minus L or whatever, you see a file, and they say that this file is, 428 bytes long or something like that, okay? The file just have the content, the content of the file is just the data. Okay, so when you open up the file, all you see are data. There's no structure. Well, it depends on what kind of file it is. If it's a Microsoft Word file, of course, it has structures in them, but only the application that knows how to deal with that particular file structures know how to open it. Know how to read and read from that file. Okay, otherwise, the file actually has, it's just a collection of bytes. Okay, so in Unix, it's very different from Windows. In Windows, the file extension means something. Unix, the file extension means nothing. Okay, every file is just a file of binary data. Okay, so it depends on what program is reading it. If the program understands that format, then it can do all kinds of stuff. If the program doesn't really understand that format, then you can still open the file and read from that file. Okay, so that's sort of one major difference between Windows and Unix. I guess on the Mac in the good old days, every file contains multiple parts. So if you want to open a file, there's a file.data for the raw data bytes for that file, and then there's also a file.resource or something like that. I guess on the Mac they call it the data fork and the resource fork, and every file is a collection of actual files sitting on the disk. Okay, so different operating system might decide to implement files in a slightly different way. Okay, but Unix, the data file is just a collection of raw data bytes. All right, and when I say bytes, so you look at them as an 8-bit quantity, and you read and write them 1 byte at a time using the read and the write system call. All right. Okay, so given that this is what a directory look like, how do you get to a particular file, right? If you want to call open, okay, you say open/home/bc/foo.c. Okay, how many file system operation is it involved? Okay, so the way that you go about doing this is that you have to parse the string that tells you this particular so this is called a path to a file. Okay, so it's sort of a directions of how to get to a particular file. Okay, so the way that you have to parse this, and you have to implement this in kernel 2, is that when you see a path like this, okay, you have to parse it by one part at a time, and then finding the directory separator in this particular file, in this particular string. Okay, so you start with the top. The first character is /, which means that you have to go to the root directory. So where's the root directory? Well, you sort of have to know where the root directory is, right? If you have a tree, you better know where the root is, otherwise you can't find anything else in it. Okay, so you know where the root directory is. You go to the root directory inode, and it looks like this, right? Okay, and then inside this directory, what are you looking for? Well, you're looking for a string named home, right? Okay, so again, the directory just maps strings to inode number, right? So over here, you go to look for the string. This might be a linear list. You go down a linear list, look up to string compare with every entry over here. When you find home, this is going to be the inode entry that you use, and you're going to use that to open the inode. Okay? So the next step is that this one will map to somewhere on the disk, right? So you make a lower level system call, you pass it down to the lower level, it says, give me that inode, right? You go to the actual file system, which know where this particular inode is stored on the file system, right? Because the lower level file system maps the inode to the disk block. Okay, so they will return that to you, and when you open it up, you say, oh, it's a directory. Okay, so therefore, I know what to do with directory. The directory are, key value, pairs, right? So therefore, I'm going to interpret /home, right, this inode number, okay, as a data structure like this, okay, and the next thing I'm going to look for is the string BC. Okay, so inside over here, the entry name are not the, full directory path. It's just the local path name inside that directory. Okay, so over here in /home, this inode, you're going to see strings that only has this part, right? Again, you go down this list, look for something called BC. Okay, you find BC, and then this will give you an inode number. And then you give the inode number, you make another file system call. All right, and this one will again lead you to another directory. Okay, and this directory /home/BC represented by inode. You open it up, say, oh, it's a directory. I know what to do. I'm going to look down over here, look for a file foo.c. Okay, so again, you do string compare. When you find this one, and then you finally find the inode, okay, and this one, when you open it up, well, then you realize that it's not an inode. Sorry, it's not a directory, it's just a file, so therefore you go read the raw bytes of that file. All right, so later on when we get into chapter 6, we're going to see exactly how the representation goes to go from a inode to a particular file. Okay, but at this time we're sort of at the higher level, at the BFS level. So in order for you to find something like this, you have to go down this path. Okay, so open. Now you can see why open is a very slow system call, right? Because the entire thing is happening in the kernel, right? So you don't have to go through between the user space and the operating system. You make one transition into the operating system. In the operating system, you're going to walk down all these data structure. Sometime you have to go to the disk to read and wait for the data to come back. And then you find out another inode number, and you have to go to the disk again, and then wait for the disk to complete. Okay, so this system call can take a long time. Okay, so the open system call is the one that takes a long time, and that's why we sort of cache all this information into the system file table, because once you open it, you don't want to do it again. Right? So all the information are cached in the system file table, including how you open this file and where is the current cursor position. Right? So remember in the system file table, right? There's an entry, the cursor position right over here. It tells you where it is. So next time when you try to call this file is being open already. So therefore, you have the inode number, you have everything about it. Now just go and read starting from a particular offset. All right? So this way the file system can be accessed in an efficient way. Okay, so the open takes a long time. Read and write, well, sometimes when you try to read data, it might incur a disk read. Okay, so that can be slow. Okay, but when it opens, it might incur many, many disk read because you have to walk down the entire path. All right? Okay. All right. The Unix directory hierarchy is basically a tree, right? I mean, the picture that I showed before, it's a hierarchy, it's a tree. But there's a way to break the tree structure. Okay. And there are two ways to break this, the tree structure. One is called hard link, okay, and the other one is called soft link or symbolic link. Okay, so hard link is kind of more basic to the file system, so the idea over here is that when you have a link, you create a reference to a file. Okay, and this is, I guess, for some reason, Unix make this restriction that when you have hard link, when you want to link to something, you cannot link to a directory. You can only link to a file. All right. So this way, one file will appear in multiple directories. Okay. There's a system call called link link that you can create a hard link, and also in the login shell, you can use the ln command that can create a link to a file. So the idea over here that there's a file, and over here there's a directory that owns this file. And now you can go to another directory and create another link. Okay, so when you do this, it's no longer a tree hierarchy, right? Because now you have something that's shared, and that's really not allowed in a tree hierarchy, but Unix allows you to do something like that. Okay, the second type is called symbolic link, and we're gonna see what it is. Okay, it's slightly different. All right, so hard link over here. So you can also use the, you can use the, your login shell command to create a link. You say ln/unix/etc/image. Okay, so this command will create a hard link to this. Okay, and the name of the hard link is going to be image, and image is going to be inside this directory. Okay, so what happens is that you go to /etc. Okay, and now you create a link, and this image will point to the same file as in /unix. All right, so /unix now have two things that point to it. Okay, so of course you have to, inside the file system, there's also a reference count. When you have multiple references to a particular inode, you have to, when you add a reference to a particular inode, you have to bump the reference count. Okay, and then eventually, when you start removing all the links to this particular inode, the reference count go to 0. Then at that time, you're free to get rid of this because nobody knows, nobody's pointing to this anymore. Okay, so they also use reference counting. All right, so why would you want to do something like this, right? So one of the things is to break, directory hierarchy, so you can have a shortcut to a particular file. Okay, so now this particular file now has two names. One name is /unix, and the other one is /etc/image. Okay, so now after you do this operation, if you look at the file system and you say, well, what was there first? Was /unix was there first, or /etc/image was there first? You can't tell, okay? Because what happened is that over here, you just have a reference to this particular, file, and it's just an inode reference. So you sort of lose that information of what did you start with, okay? So I guess the next page is the picture over here, okay? So when you want to create this particular entry, right, you want to run this, run this shell command, okay? Inside the operating system, you have to implement the link system call. What you would do is that you will go to /etc, okay, add an entry called image over here, and then copy this inode, okay, copy this inode to be right here. Okay, so over here, right, this dash line over here says slash etc. is inode number 4, right? So you follow inode number 4, so this is slash etc. Inside over here, that's where you will add an entry. You can call it image, right? And the inode number over here is an exact copy of whatever that you had before. Okay, so all it does when you implement this link system call is to add an entry and then have it point to the same inode. You don't do anything to the actual file, you just make a reference to it. All right, so after this picture has been established, right, if you look at the file system and you say, well, who was there first? Slash Unix was there first, or slash etc. slash image was there first, or inode 117, where did it come from? We have no idea. Okay, because once you do the link operation, then these two things look exactly the same. All right, which is different from soft link. Soft link, you can it's sort of a directional thing. You can actually figure out who was there first and who was there second. Okay, so once you do something like this, what if you remove this link? Okay, I create ln slash Unix slash etc slash image, right? And then I say rm slash Unix. Okay, all right, slash Unix, right? So in that case, I remove this link. Okay, so again, if you want to implement remove, what you do is that you go to the you go to the directory, you delete this entry, right? Unix over here, you just get rid of it. Okay, when you get rid of it, well, 117 is still pointed over here, right? The reference count goes to goes to 1. Okay, so it's still reachable. So if you do these two things consecutively, this is exactly the same as moving a file from one directory to another. Okay, so therefore, when you do a move, I guess on Unix command there's a move. Move is implemented by two operations. One is do a hard link, and then the other one is to remove the previous link. Okay, so moving stuff in Unix is actually very fast. All right? All right, what about soft link? Okay, so soft link is directional. Okay, so over here is ln, and on the command line, if you want to do a soft link, you say -s to say I want to create a symbolic link. Okay, I want to create a symbolic link to the slash Unix file, and this link is going to be in slash home slash bc slash mylink. Okay, so slash home slash bc, you will go to this place, home bc. So what you do is that you create a new entry. In this case, you're going to create a special file. This special file is not a device, but a different kind of file. So this file is called a symbolic link. Okay, so you're going to create a new file, and inside this file, you're going to copy the string slash Unix inside this file. All right, so what happens is that if you open this particular file, you go to slash home slash bc slash mylink. If you make this open system call, okay, the open system call will realize that this is a symbolic link. So instead of opening this file, it will open this file instead. All right, so in this implementation, right, you go all the way down here, you find mylink, and you open it. There's another path in there, and you have to start all over again. Start from that and find the exact inode number, and that's the one that you open. Okay, so this one is more of a convenience, okay, so that you can have, all kinds of, because sort of a hierarchy is really inconvenient. If you have a file you keep wanting to access, it's easier to just create a symbolic link so you can, easily access it from a shorter path. Okay, so this, I do that all the time, because I hate to type something really long. All right, you can also, one good thing about symbolic links is that you can do a symbolic link on a directory. Okay, so I can do a link slash home slash bc slash etc slash bc. Right, so in that case, I'm going to create an entry slash etc slash bc, and inside this file, I will put in, or inside this special symbolic link file, I will put the string slash home slash bc into it. And again, if I open slash etc slash bc, it will notice, the operating system will notice that this is a symbolic link, and then it will open this thing instead. All right. So I guess one major difference between symbolic link and hard link is that symbolic link, you can use that on a directory. Okay, and hard link, for some reason, is not allowed. All right, the other important thing that's used in Unix is the concept of a working directory. Okay, every process, okay, So every process in the kernel, it maintains what is the current working directory for a user process. Okay, so this doesn't really apply to kernel processes, just user processes. So the idea over here is that if you want to open a file, okay, you're going to give so if you make this open call, right, open, and then the first argument is a path, okay. If this path starts with a slash character, okay, then you are giving an absolute path for a file you try to open, okay. But what if this doesn't start with a slash? It starts with something else, okay. So the way Unix works is that this directory is going to be relative to the current working directory that's stored inside the kernel, okay. So if the current working directory is /home/bc, okay, you try to open xyz or xsy/z. What happens is that these two strings will be concatenated together. So you will be opening /home/bc/xxy/z. All right. So if the first character is not slash, then you concatenate them together, but you also have to add a slash between them. And this is the actual file that you want to open. Okay. And again, this is sort of for convenience. When you try to open a file, you can open a file relative to the current working directory. Okay, and the current working directory for every process is stored in the kernel. So where would you store it? You store it in the process control block, right? People probably have seen this already. In the process control block in Unix, there is a current working directory. Okay? All right. So if your user application wants to find out what is the current working directory for the process, you will make a system call, get current working directory. As it turns out, there are several different versions of it. Different Unix systems, different Linux actually have different things. If you want to change them, you have to use the change directory system call. Okay, on your login shell, you can also use the cd command to change the current working directory of your login shell. Okay, so that's why when you are, when you log into Nunkey, right, if you say cd to another directory, now when you type ls, if you don't give any command line argument to ls, it will list the directory content of the current working directory. Okay, and how do you implement ls? Well, you open up the directory inode of the current working directory, right? And the name of the current working directory is what? Right? Is dot, right? Okay, so even if you don't know where you are, right? If you want to find out what's in your current working directory, right? You can open dot. Okay, this character doesn't start with a slash character, so therefore you're going to concatenate /home/bc/dot. That's going to be the directory that get open, right? So if we open this directory, can we find out the content of the current working directory? Yes, right? Because we know that this one maps to an inode number that's corresponding to the current the directory that you're in. Okay, so this actually works. That's why we have a dot entry. Because anytime you wonder where you are, you just access the dot directory, the dot directory entry. All right. If you want to change directory, you use this command, and this will eventually make the system call to change the current working directory for your process. Okay. If you want to show the current directory in the login shell, you can use the Unix command pwd, and that will print. As pwd basically, depending on what version of Unix you have, they will make the right system call to find out the current working directory of your process. All right? Okay, and then, the same thing happened, right? When you process, fork, and create a child, this information is passed on to the child. Okay? So that's why in your login shell, when you start running warmup 1 and 2, if the warmup 1 and 2, in the beginning, you call get current working directory, it will know where it is, right? That's the directory where you start, running these programs. Okay, if warmup 1 and 2 is installed in the system area, like installed in /bin, and if you are sitting at one directory and you say /bin/warmup1, okay, and then if you read the current working directory, it's going to be wherever your current working directory is for your parent process. When it creates this child process, it passes that information on. Okay, so when you launch this command, the working directory is not /bin, it's wherever the parent's working directory is. And the parent, in this case, will be your login shell. All right? Okay, so the next thing we're going to talk about is access protection. And I think this doesn't really apply to Unix. Unix is kind of a toy operating system. You only run one user at a time. So even though in kernel 3, we're going to implement user space and the kernel space, but the user process, there's no login procedure. when you are in user space, you are logging as a default user. Okay, so this really doesn't apply to kernel 2 or 3. But it's a sort of important concept of how does the file system protect itself against other users, right? On Nunkey, when you create the stuff in your own directory, if other students try to look into your warm-up 1 and 2 solution, they won't be able to see your files, and that's a good thing. That's because Unix has some way to protect these files. Okay, so we're going to see how this works. So Unix and many other systems, they associate with every file some indication of which security principle are allowed access. Okay, so every file sort of come with a permission that you grant to other, over here it says security principles. What are security principles? So on a machine like Nunkey, right, the security principle are running processes. Okay, so when you secure shell to Nunkey, okay, you're sitting in front of your machine, right? You secure shell across the internet to Nunkey, so clearly you are not sitting at a console of a Nunkey, terminal. Okay, you are, you're sitting somewhere else, right? So when you log into Nunkey, who is actually logging into Nunkey? So of course, what happened is that, so let's go back, right? When you have the operating system, when the operating system finish initializing themselves, going to the idle process, right, like in your Unix assignment, what does it do? Right, it brings up a shell, right? Okay, it brings up a K shell in kernel 1. Okay, so same thing on a machine like Nunkey, right? When it boots all the way up, the operating system actually has nothing to do. Okay, so what it will do is that it will bring up this login shell, okay, and try to, a login screen, okay, and trying to wait for user to connect to them. Okay, so in this case, that connection is set up by secure shell, right, SSH. So when you secure shell to that, you're talking to an rlogin daemon, right? We saw rlogin before. Rlogin is just something that sits there and then passes information between you and the operating system, okay, and what does it try to do? Well, it asks you for your user your login ID and your password, right? So once you provide your credential, that information is sent to the operating system checks that you are the right person, and what it will do is that it will create a login shell on your behalf. Okay, so when you log into Nunkey via SSH, right, eventually they run this program, right, /bin, maybe /user /bin /tc shell. Okay, so after the remote login daemon logs you onto Nunkey, right, the Nunkey kernel start this process on your behalf. Okay, because you provide a credential to say that, hey, I am who I claim I am. So therefore, here are my credentials, right, user ID and password. And then, once they verify that, they create a login shell, and this login shell will be logging with your, identification. Okay, so from this point on, this login shell, okay, is running with your identity. And from this point on, if you fork a child process, right, your child process will inherit the identity from the parent process, and the parent process is this one. Okay, does this process, when it runs, does it inherit parent, the identity from the parent process? No, right? Because, the parent process is actually the login shell, and the login shell is run with the root privilege, right? It's the most privileged, thing on Nunkey. So you cannot, as a user, we don't want to run at that level, or the Nunkey doesn't want us to run at that level. So therefore, when it, create this login shell on your behalf, you're it's in the kernel, so you can actually change the identity of that program from root to your identity. Okay, so once this guy is running from this point on, if you create any child processes, right, by doing fork, all the fork will start with your identity. Okay, so this is the identity. It's also over here that will give you, that's how you identify who can access something. All right, so once you log in over here, you identify you as yourself, and every user on Unix has a user ID. I think on Unix, the default user ID is what? Is 500 or 1,000? Anybody knows? I can't remember. So if you look at your login credential on Ubuntu, I think you'll find out your user ID is either 1,000 or 500. Okay? So every user is identified by a single number. All right, so a security principal is normally a user, okay, and that user is configured into the operating system so that, Nunki will say that, yeah, your login ID is allowed to log into Nunki, and this is the credentials, the password that needs to be used in order to log into Nunki, okay? The other kind of security principal is called a group, okay? On Unix, there's a group of users, okay? So I think our login on Nunki, our user ID is also our group ID. So we are in the group of ourselves, and there's nobody else. But on a Unix system, you can actually create a group. You can say that, well, these 50 students, they belong to the CS402 group during the summer. Okay? So in that case, you will also get a group identifier with a group ID, saying that, the CS402 group is group identifier, I don't know, 1050. All right? So when you access the file, every process will carry with them these two kinds of ID. One is called the user ID. The other one is called the group ID. Okay? So every time when you try to access a file, open a directory, the operating system will use that information to determine whether you have access or not. Okay? All right, so each running process can have several security principles, right? I mean, you start with 2, okay? But in some Unix system, like Nunki, every user can belong to many groups, okay? In 6th edition Unix, every user can only belong to one group, okay? And Unix, doesn't even really have users, so it's even simpler than that. All right, so every file is associated with the set of access permissions, okay? And the access permission are given for one type of users, okay? So as it turns out that there are 3 classes of principals, okay? One is called the user, and the user is the owner of that file. So every file belongs to, belong to a user, and it also belong to a group, okay? So there are 2 identifications. One is the user, and the other one is the group. The group is the group owner of the file. Okay, so if you do a ls minus l, let's say do a ls minus l warmup1. Okay, so this is the executable warmup1. Okay, what you're going to see is that you're going to see that you own the file. You will see your login ID in the output of this command. I think if you do the ls minus lg, that means that you want to see, the user information and also the group information. It will show you 2 things. One is who owns this file, and also which group owns this file. Okay, and I think on Nunki you'll see both are the same as your login ID. All right, but remember that can be changed. And then for everybody else, there's something called others. Okay, so for every file, they want to specify that, the owner of the group will have these kind of access, the group owner of the group has these access, and then everybody else has a different access. Okay, so if you create a file, then this file is the group CS402, okay, on Nunki. Then in the group access, what you will allow is that everybody in the CS402, they all have the same access to this file. Okay, so maybe that's not what you want, because if you create a file, for your warm-up assignment, you don't want anybody else to see it, right? So sometimes, so you have to be very, very careful with these group permissions. Okay, so that's why on Nunki, by default, you are in only one group. Okay, and later on, once you create a file, by default, that file will belong to you and your group only. If you want to allow access to everybody else in the group, what you can do, you can change the group of that particular file. Okay, so that will change the group ownership of that file. All right? All right, so what kind of operations are allowed? So the operation, as it turns out, also are grouped into 3 different classes. One is that, so when you do ls minus l, you will see the following. You will see one character in the beginning. So for a file, you will see a dash. Okay? And then followed by possible things are RWX, RWX, RWX. Okay? The first 3 letters correspond to the user. The next 3 letters correspond to the group. And the last 3 letters correspond to others. Okay? So for the user, there are 3 different kinds of accesses. There's the read access, there's the write access, and then there's something called the execute access. Okay? For the group, there's read, write, execute. For everybody else, there's also read, write, execute. Okay? So if you see a letter R, W, or X, that means that you have the right, okay, to perform that operation. Okay? If you don't have the right to perform that operation, instead of having R, W, X, you will see a dash. Okay? So it is possible you will see something that the first character will tell you what type of file this is, If it's a regular file, it will be a dash. If it's a directory, it will be a D. If it's a symbolic link, it will be a S, and there's some other, characters. Okay, so if you see something like RWX dash 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 dash, that will mean that the owner can read this file, can write this file, can execute this file. So even though the file are not executable, it's okay to say that the file is executable. Okay, and these 3 dash means that everybody in the group will have no read, have no write, have no execute access. And finally, for everybody else in the system, on Nunki, right, they will have no read, no write, and no executable. Okay, so most of the time when you create a file, this is probably what you need. Okay, you don't want other people to be able to see your files. Okay, but they can be changed. All right, so read, it can read a file or a directory. Write, you can write a file or a directory. What does it mean to write to a directory? Right, so remember, a directory is just a mapping of strings to inode, right? So to write to a directory means that you want to add entries into it, or you want to delete entries from the directory file. Okay, a regular file, you can read-write to it, the regular way. Finally, execute. Okay, so if you have a file that's not executable, right, your warmup1, after you compile it, it's executable, so you can run it. You can say /warmup1, right, /warmup1. So again, what does that mean, /warmup1? Right, it means that, you use the current working directory, you add a slash to it, and you append this, and then you pass this one to, you do fork and you do exec. All right, so that's what /warmup1 means. Okay, what if your file is not executable? What if it's a directory? Okay, over here it says one must have execute permission for a directory in order to follow a path through it. Okay, so over here, let's say that if I change this one to X and change this one to X, okay, so let's say that this is a directory entry, so the first guy is going to be a D. Okay, so this means that the owner can read and write and execute, this directory. The group can read and write and execute this directory. Cannot read, cannot write, but they can execute this directory. And everybody else, they cannot read, cannot write, but they can execute this directory. Okay, so execute a directory meaning following a path through it. Okay, so that means that when you get that string and you try to look for an inode, okay, if that directory has the corresponding execute bit set, that means that when you perform the open system call, you're actually allowed to follow that path through that through this directory to look for stuff at the lower level. Okay, so that particular operation, I guess you can call it the lookup operation, right? When you get an open system call, the first thing that you need to do is to look up from a string, a full path name, or to have a full path. Okay, you want to look up the corresponding inode number. Right, so when you open a particular file, the first thing you have to do is to look it up. Given that string, what is the corresponding inode number? Okay, so what you want to make sure is that every directory along that path will have the execute bit set. Okay, if any one of them don't have the execute bit set, then you will not be you will not be able to open the file because you have access protection violation that you don't have access to a particular directory. All right, so that's where you need to check all the execute bits for every directory along that path. All right. So as it turns out that there's actually a rule for checking these permissions. Okay, you have to done in a certain order. So if somebody wants to open a file, right? So you first of all, there are two parts, right? One is that you need to determine whether the security principal that's trying to access this file, is it the user or is it the group or is it anybody else on the system? Okay, and then you have to decide whether you're going to grant read, write, or execute privilege to that security principal. Okay, as it turns out that you have to do things in that order. Okay, so you got to first you determine the smallest class of principal the requester belong to. Right, so a process comes to your system and asks for to access a file. Okay, so first of all you need to determine who is it. Is the person who's requesting to access this file, is it the owner of the file? Is it the group owner of the file, or is it everybody else? Okay, so what that will do is that will narrow down which 3 bits you have to look at. Okay, if you determine that that security principal is the owner of the file, then you need to look at these 3 bits to determine whether you want to grant permission to that security principal or not. If you determine that that security principal turns out to be the group owner of this file, then you only use these 3 bits, you ignore everything else, and you use those 3 bits to determine whether you want to grant access or not. Okay? If the security principal is neither the owner nor the group owner, then you use the last 3 bits to determine whether you want to grant access or not. Okay? So you're going to do this in this order. First, test if it's the user. Okay? If it's not, then you test if it's the group. And then if it's not, then you determine that it's the other. Okay? So you got to determine this first, and then you check the appropriate permission for that, with that class. All right? Don't do it the other way. You have to follow this, this particular rule. Okay, we're going to see some example of how this is applied. Okay, some of these things are a little counterintuitive, and that's because we have to follow that rule. Okay. All right, so we do a ls minus lr. R means recursive. Okay, we're starting from the current working directory. We're going to recursively down all the way to the bottom and show the information about all the files there. All right. So the directory structure is that we have a current working directory over here. Okay. It has 2 subdirectories. One is called A. The other one is called B. Inside A, there's a file X. Inside B, there's a file called X and Y. Okay. So clearly, this X and this X are not the same. Okay. They're different inode numbers. All right. So if we do ls minus lr, right, we're going to see that the directory A and B are right here. Okay. In this example, right, this first letter is D because they're directories. And then the first 3 bits over here are RWX for the owner. But the next 3 bits are different for directory A and B. And also the last 3 bits are different for the directory A and B. Okay? It also shows that this is the user, or the user, okay, or the owner of that file. And then over here, this is the group of the group owner of that file. Okay, the group owner. All right. In this example, we're gonna assume that Bill and Trina are members of the ADM group. They're administrator, okay. And Andy is somebody called Andy, and Andy is not, is not a member of the administrator group, okay. And this directory belongs to the ADM group, and so is this directory, and it belongs to the user Bill, okay. And then over here, inside the subdirectory A, there's only one file. Okay, and it's a regular file, right? First character is dash, and then this is, user, this is group, and this is other. Okay, it's owned by Bill, and owned by the ADM group. Okay, and then the rest are, this is the size of the file, and this is the last time the file was written to. Okay, all right. In the B subdirectory, there are 2 files, X and Y. X belongs to Bill, and then also belongs to the ADM group. Y belongs to Trina, and it belongs to the ADM group. Okay, and their permissions are different, in this case. All right, so let's go through this and look at this, try to answer some of these questions. All right, the first example, may Andy list the content of directory A? Okay, so first you determine who is Andy. Okay, is Andy the owner, the group owner, or others? Okay. Directory A is this object, right? Directory A is this object, okay? So therefore, you come to this directory A, the owner is Bill, and the group is ADM, right? So first, you look at Andy. Is Andy the owner? No, right? So you have to ask the most specific one first, and then, go to the less specific one. So first question, is Andy the owner? No. Is Andy the group owner? No, right? Because Andy doesn't belong to the group, okay? Doesn't belong to the ADM group. So Andy belongs to the other category, so therefore, in this case, you have to look at the last 3 bits, right? Because the first 3 bits is these 3 bits is the owner, these 3 bits is the group, and the last 3 bits is the owner. Okay, so over here it says Andy. Well, if Andy wants to list the content of directory A, what does Andy wants to do with A? Well, Andy wants to read it, right? You open the file, you open the directory inode, you read the entry, and you display them. Okay, so in this case, read, well, Andy is not allowed to read it. Okay, so therefore the answer is no. Okay? Okay, so in this picture, I'm going to highlight exactly why the file system denied access to Andy. Okay, it's because of these 3 bits, and that's why Andy was denied access. All right? Next example, may Andy read a/x? Okay, so again, when you try to open a path, right, you got to go to this directory first, open this entry in order to find out what the inode number is for x. Okay, so first you have to access directory A. Okay, so what does Andy wants to do with A now? Well, Andy wants to follow a path through directory A. Okay, Andy doesn't really want to do a list directory content of A, and those two are different, operations. Okay, so in this case, Andy only wants execute permission for directory A. All right, so again, you go back to this entry, right? You said, well, who is Andy? Is Andy the user? No. Is Andy the group? No. Is Andy others? Yes. Okay, so therefore, we're going to look at the last 3 bits. Okay, so Andy wants to follow a path through this directory, so Andy is allowed to do that, right? Because over here, the execute bit is set for the directory, so Andy is allowed to go inside. Okay, I mean, Andy is not allowed to go inside for a particular file. Andy is not allowed to go inside and look around. Okay, if Andy wants to look around, it needs the read privilege over here. If Andy wants to access a particular file, so which means that Andy knows that under this directory, there's a file called X. Okay, so that's a different kind of privilege than want to look at the entire directory content of directory A. Okay, so Andy is allowed to execute over here, and then the next guy is going to be X, right? And we have to do it all over again. We have to ask for this file, is Andy the owner? No, Andy is not the owner. Is Andy the group? Andy is not the group. So Andy is others, so therefore you look at these 3 bits. Okay, so Andy is actually allowed to write to this file. Okay, so it looks kind of weird, right? Because over here, Bill owns this file, owns this directory, but inside this directory, there's a file Andy can actually modify. Okay, Andy cannot do anything at this level, but this file, Andy can actually change it. Okay, so the answer over here is yes. Okay, because Andy's allowed to access it, right? So if I want to highlight something, I'm going to highlight all these 3 bits to say that's why Andy's allowed to go to go follow a path through directory A. And this is why Andy is allowed to write to that file. All right? Oh, actually, over here, does Andy read it? Of course, Andy is allowed to read it. Example number 3, may Trina list the content of directory B? Okay, over here, you come to directory B right here. Okay, who is Trina? Is Trina the owner? No. Is Trina the group? Right, Trina is the group owner of this file. So therefore, you look at the middle 3 bits. Sorry. The middle 3 bits right here. Okay, so the middle 3 bits says that Trina can list the directory content of B. All right? Okay, next example. Can Trina modify B/Y, right? B over here. Trina is not the owner, but Trina is the group, so you read these 3 bits over here. Okay? So now, what does Trina want to do with this directory? Trina wants to follow a path through it, and Trina is denied access.
The time is
right
23 o'clock.
Okay? In order for Trina to follow a path through this directory, you need an execute bit right here. So therefore, Trina got stopped at this level, even though if you look at over here, if you look at down here, why? This file actually belongs to Trina. Okay, so you think that Trina should be allowed to do something to this file, but Trina is blocked not because of at this level, but Trina was blocked right at this level. Okay, so therefore, Trina cannot access that because of these 3 bits right here. All right. May Bill modify B/X, right? Bill come over here. Bill is the owner, right? So therefore, you're going to look at these 3 bits, RWX. So Bill can follow a path through it, right? So B is okay. B/X is right here. Okay, again, you start all over again. Is Bill the owner? Yes, Bill is the owner. And then look at these 3 bits. Okay, is Bill allowed to modify it? No, right? So even though this file is weird, right? Even though the group can modify it, everybody else can modify it, but Bill is the only one that's not allowed to modify it. So too bad, right? But turns out that Bill can easily change the permission of this file, okay? Because if you are the owner of a particular file on Unix, so Unix is a kind of system that if you are the owner, you can actually change permission on anything you own. Okay, so Bill can actually go over here and change it to right, and then it'll be okay. Okay, but at this point, Bill cannot modify that file. All right? All right, so no because of these 3 bits, right? Okay, finally, may Bill read B/Y, right? B is right here. Bill is the owner, no problem. Come in here, right? And come to B/Y, this guy, okay? And again, you start all over again. Is Bill the owner? No. Is Bill the group? Yes. You have to look at these 3 bits for the group. Okay, so again, this setting is weird, right? You know, Trina owned this file. You know, everybody in the group don't have access, but everybody else in the world has access. So you say, well, how come, you know, I mean, the group is a subset of everybody else in the world. So how come if everybody else in the world can access, how come the group is denied access? Well, because we have to follow that rule, right? Right? The rule says you determine who the security principal are and only focus on those 3 bits. You ignore everything else. Okay, so that's why in the end, you know, Bill is denied access to read this file. All right. Okay. You know, you can go muck around with your files on Nunki, you know, but make sure you only do that for files you don't care if other people see them. Right? Usually, I think by default, when Nunki create a new account for people, they will have you know, rwx -- in your home directory. Okay, so which means that, you know, anybody else, if you want to grant access to any the file inside your home directory to anybody else, well, they have no access. Okay, even though they know the file name. Okay, so if you want to give a particular file to other people, so they have access to it, you know, you got to make sure that you change this into X, so at least they will be, if they know the file name, they will be able to access it. All right, so how do you share a strange file, you know, with your friend? So one thing you can do, you can name your file with a really, really weird name, so nobody can guess it, right? So if they can, you know, look at a directory listing of your home directory, but if they know that really weird name, they will be able to access it. Okay. All right. Open system call. This is one of the system call you have to implement in kernel 2, and this is like one of the most complicated system call in kernel 2, because again, open is where you have to do a lot of work, right? You have to walk down the directory, look up the entry, map that string into an inode number, and then you have to do many, many mappings before you eventually get to a particular you know, file. Okay, and then you have to, you know, make sure that you have access to that file. Okay, so open, right, takes one argument, is the path, and this path, if it starts with a slash, then you start with the root directory. Otherwise, you start with the current working directory. Okay, and then over here is how do you want to open it? You can open the file for read only, for write only, for rewrite, for append, to create a file. So when you want to create a file, you got to make sure that that entry doesn't exist. Okay, when you should create something. Other stuff is open the file for exclusive, you know, read. So this one meaning that if you have a file that is going to be shared by multiple people, if you have exclusive, you know, open it in exclusive mode, you got to make sure nobody else is accessing it. Okay, so I think Unix you don't have, there's no such thing. But in a lot of the operating systems like Windows and, you know, Unix, you can have a file, open a file for exclusive access. I think Windows go kind of overboard with exclusive access. Every time you open a file, they make it exclusive. There's something called trunk. This one you open it for trunk, and then you want to truncate the file. So this one you open it, and immediately we have to open it with write permission, and you want to truncate the file to size 0. Okay, so no matter how big the file is, it will shrink it down to 0. So by the way, I just want to mention that in kernel 2, because we always get a lot of question about, you know, this one in kernel 2. In kernel 2, I think there's no way to test it. So even though you're supposed to implement otrunk, but since there's no way to test it, you probably should not implement it. Okay, because our requirement is that anything you implement, you have to test it, and if there's no way to test it, then that will be tough. Okay, so you don't have to implement this. There are other things that when you open, you can also so all these you know, options, they are a single bit, so you can actually OR these things together using the logical OR operator. Okay, you can also actually open a file for non-blocking mode. Okay, when you open a file for non-blocking mode, from this point on, if you try to read the file, the read system call actually returns right away. If it turns out that, you know, the data is not available, it's going to set this E would block or something like that. You know, in the error number, so you know that this one was not successful, and you're supposed to, you know, wait for I/O completion before you get the data. Okay. So anyway, so you should, I guess in our class, you should never use something like this because that's kind of, I guess because in our class, we want to make, system call like read and write. They're all synchronous. So when you make that call, you wait for the, the function to return, and when it returns, the data are guaranteed to be there. All right. Okay, so anyways, when you implement the open system call, you're going to find out that there's actually not a lot of documentation. So I think the expectation is that you do a man on open on your Linux machine and try to see, what are you supposed to do, what kind of stuff are you supposed to handle when you try to open. All right. Okay, to change the file permission, right? The owner of the file can always change the file permission. So over here, you can say there's a system call called chmod. Okay, so this one will modify the file permission. So again, you specify a path, and then over here you specify a mode. Okay, the mode is a numeric value. So as it turns out, that this is one of the common place you will use the octo number in the Unix system call. Right, normally we deal with decimal number and then sometimes hex number when we try to do a hex dump. We really use octo representation of a number. But in this case, since we have RXW, right? RWX. Okay, so this is 3 bits, right? So you can actually represent by a binary number, 111 if all the bits are turned on. If all the bits are off, then it's a 000, right? So this one will be 1 digit in an octo number, right? Octo number go from 0 to 7, and then you have to do a carry and go to the next digit, right? So you can actually specify this. If they're all turned on, then this is 777. Okay, in the C compiler, if you want to tell the C compiler you're using an octo number, you have to start with the number with the 0. Okay, so if you start a number with like this, the compiler will know that you're dealing with the octo number. Okay, if you're using a hex number, right, you have to say 0x, AF or something like that, right? Okay, otherwise, if you just give a bunch of digits, it's going to be treated as a decimal number. Okay, so over here, so what it shows over here is that there are also these Unix, macros or pound defines that can be used for these values. So you can use the IR user, to turn this bit on. You can use IW user to turn this bit on. You can use IX users to turn this particular bit on. Okay, and similarly for the group, there are these 3 symbols to use individual bits. And you can OR them together, right? OR them together, right? So if you want 111.000.000 or RWX --, then what you will do is that you will OR this with this, and you're going to get these 3 bits. Okay? So these 3 bits, you can pass it to the mode over here. All right? Or you can just say, I want to say chmod. Okay? And given a path, you just say 0700, and that will be the same thing as turning these 3 bits on. All right? Or you can say, 711, and that will be RWX --x, right? Because these are 1 bits, and all the dash are 0 bits, so this is 711. All right? Octo number is a little weird, but when you use change mod, that's what you can do. Okay, and also the chmod you can use as a command line, in Unix. So when you are in your login shell, you can say chmod followed by a path, and you can just use these numbers 0700. That will actually work. Okay. All right. To create a file, you can use open, and there's actually additional system call called create. So you can also use that. But usual way is to do open. Okay. When you try to when you try to create a new file, what Unix will do is that, this open system call, it tells you when you try to create a file, it will use the 3rd argument. So where does the 3rd argument come from, right? Open only has 2 arguments, right? It has 1 argument, 2 argument. So it turns out there are 2 different versions of open. When you call open with only 2 arguments, then, only these 2 will be used. If you call open with 3 arguments, the last argument, they're expecting the mode to be in there. Okay? So what happens is that, this mode will not be used directly to create that particular file. What happens is that, there's something called the user mask. The user mask will be applied together with this mode to create the access permission of the newly created file. Okay, so it will take this value over here and perform a logical AND with the bitwise inversion of the user mask. Okay, so if the user mask is, let's say the user mask is 777, okay, which means in binary representation it's going to be 111, 111, 111, right? This is base 2. Okay, if you say twiddle this, okay, which means that it's a it's a bit flip on every one of these bits, then that's the same thing as saying it's 000, 000, 000, 000, okay, in binary. And if you do a logical AND, right, you're going to end this with any mode. Well, if it's a 0, then every bit is going to be set to 0, okay, because this is a logical AND for every bit. If you AND 0 with anything, you're going to end up with 0. All right? Okay, so let's see some example of these user masks. Okay, this user mask. So what happened is that when you are, let's say that you're the compiler, okay, and you try to create a new file, right? When you finish compiling, you're going to generate warmup 1 or warmup 2, right? So you're creating a new file. Okay, so when you call create, you're going to specify a mode, and usually for compiler, the mode, the third argument in open is going to be 0777. Okay, so which means that it's 111, 111, 111. Okay, base 2. Right, so the intention there is to perform a logical AND of this mode with the inverse of your user mask. Okay, so what is the user mask, right? So on your Unix login, okay, you can actually saying, oh, no, sorry, there's a command called umask, I think, okay? Umask will print out the current user mask, okay? I think that's the command, right, over here. Okay, so so you'll print out your current user mask. So for example, I think on Nunkey, by default, the user mask is equal to 077. Okay, so 077, right? Only there's 2 sevens, right? So it's going to be 000, 111, 111. Okay, so if you perform a a bitwise a flip of every bit over here, right? Twiddle this is going to be equal to 111,000,000. Okay, and if you AND this one with this one, perform a logical AND, right? Which means that every bit you AND it with the other bit. 1 and 1 is equal to 1. 1 and 1 equal to 1. 1 and 1 equal to 1, and all these other bits are 0. Right? Whenever you see a 0, well, then then they all get turned into 0. Okay, so the actual file that you create, warmup 1 and warmup 2, is going to have permission of 700, which means that only the user can run these programs. All right, which is probably what you want, right? Okay, so by default on Nunkey, I guess the system administrator set up your user account that set this one to be like this. Okay, there are other systems by default they will send it to the user mask will be set to 022. Okay, so that's 000, 010, 010. Okay, so one way to interpret these bits is that these are the bits that need to be turned off. Okay, so when you have this bits 077, that means that all these access permission needs to be turned off. Right? When you set a 1 there, you get flipped to 0, and 0 end with anything is equal to 0. So all these permissions will be turned off. Okay, so when you have a 022, that means that for the group, the write permission will be turned off. For everybody else, the write permission will be turned off. Okay, which means that if you end the, so if you invert this, you're going to get 111, 101, 101. And if you end this pattern with what the compiler produced, you're going to end up with this particular bit pattern, which means that the user can rewrite and execute this file. The group can read this file and execute this file. Okay, and the others can also read this file and execute this file. Right, so that means that you create a file where anybody can execute, okay, and also anybody can read it. What does it mean to read the file? Why does anybody else want to read an executable file? So they can copy it, right? If they can read it, they can read the content, and they can copy it into their own directory. Okay, so anyway, so compiler usually have this. When you have an editor, okay, like VI or Emacs, when you want to create a brand new file, then the mode is set to 066 because by default they create a file that's not executable. And again, this is ended with the bit inverse of the mask to create the actual access permission of that file. And then again, there's some example over here. You can play with these numbers. All right. All right, so we are done with chapter 1, and the midterm coverage is going to up to, I guess over here these are the one with X's, right? So the midterm coverage is going to be all the way to here, okay? And minus everything in chapter 5. Okay, as promised, I'm going to go to go to the class website, right? So this is posted yesterday. And you're supposed to read the exam section of the course description webpage, right? That will take you to here. Okay, look at the exams. So here are some of the exam questions, right? There will be, I guess there's no calculation type problem on the exam. So the only kind of problem you're going to get are the short, sort of the short or medium answer question. I'm going to ask you a question and you need to answer it as precisely as you could. And the second one is the multiple choice question, okay? The multiple choice question, by default, every multiple choice question has more than one answer, okay? So you need to select all the correct one, and you need to make sure you don't select any of the incorrect one, okay? When you select the correct one, you get positive points. If you select incorrect one, you're going to lose 1 point for every incorrect answer, all right? So some problems are 2 points. Right, they have 2 correct answers. So if you mark the 2 correct one and you mark the third one, which is wrong, you're going to get 2 points for the 2 correct one, and you're going to subtract from 1 point for selecting the wrong one. You're going to end up with 1 point. Okay, so those are the rules. And okay, so so when you read the non-multiple choice question, usually the question will say, in n words or less, you need to answer that question. So it's like if 5 words or less. You can write more than 5 words, doesn't really matter. But when it says in 5 words or less, it's trying to tell you that we're expecting a short answer. Okay, so if you end up giving a really long explanation, maybe you are in the, you're going the wrong direction. Okay, and also if we ask you for an answer, as long as what you write is correct, you're going to get credit for that. But if you start writing too much and you start bringing in stuff that are incorrect, okay, we're gonna take points off for that. Okay, so try to follow the hint, right? This N is a hint of how long your answer should be. It could be longer, but when you write too much, you might end up saying something that's wrong, and you may end up having a point taken away after they're given to you for the stuff that you said that are correct. All right, so for every problem, you can never go negative. So we're gonna, so if we give you some points and start taking stuff away, it's not gonna go to be, less than 0. All right, some people worry about that, things like that. All right, and also, okay, so when you read the problem, please read it very carefully, okay? If the question asks for a general question, okay, you need to give a high-level answer, okay? Don't answer a general question. It says, in general, blah, blah, blah. Don't give examples, okay? Examples are no good for a general question, all right? And if the question asks you for a very specific thing, don't give a general answer, because otherwise you're going to end up with very, very little partial credit. Okay. I also may ask you a question about Unix. Okay. So if a question doesn't mention the word Unix explicitly, okay, then it's not about Unix. Okay. So I guess in the previous exam, I always get people say, oh, but that's true for Unix. Well, I didn't ask about Unix. Okay. So if I don't mention the word Unix, don't answer, according to what you saw in kernel 1. Okay. All right. Okay, so over here, most of the Unix-related questions are very high level, but although I may ask you about the purpose and the usage of a particular field inside a particular important kernel data structure. Okay, so what is that field doing? What is the use? Things like that. Okay, but usually I'm not going to ask you what does this function do and things like that. Okay, data structure is kind of more important. All right, lecture slide. If I have a gray X on the lower left corner, that means I'm skipping those. So you're not responsible for those lecture slides and also the corresponding stuff in the textbook. Okay? Okay, so exam grading, in order to be fair to the entire class, we can only grade based on what you put down on the exam paper. We must not take into consideration what's in your mind when you wrote the answers. Okay, so you can't say, I didn't mean that when I wrote that answer, because we're going to assume, you meant what you wrote and you wrote what you meant. Okay, so I guess this sort of goes with regrade. when you regrade, when you ask for regrade for an exam. Oh, by the way, I use the term regrade. Even though if you don't want your exam to be regraded, you just want to look at it. Well, that's called a regrade. Okay, you can just look at it and don't complain, and that's also a regrade. Okay, so if you ask us to regrade something, then we're going to sort of stick to this assumption that what you wrote is what you meant, and what you meant is what you wrote. All right. Also, in general, better answer may get more points. So we try to give partial credit. Okay, so for the word problem, some answers are better than other answers. Okay, so just because your answer is technically correct, you shouldn't really expect full credit unless you get the best answer. You give the best answer. All right, and the best answer is where? Well, I'm going to say that the best answer is on the lecture slides. So if you review the lecture slides for the exam, and if you see anything you don't like, you should complain to me before the exam. Okay, once the exam starts, it's too late to say I don't like that answer. Okay, so if you don't think that that's a good answer, talk to me, send an email to me, and if I agree with you, and I will actually change the lecture slides, and I will tell everybody I changed the lecture slides. All right. All right, and also during the exam, please only ask clarification question. We don't give hints in the exam, so don't ask for them. If you ask for them, the TSA, or me, we're just going to tell you that we can, give you hints. All right. Okay, so make sure you're familiar with this, and these are the rules that we're gonna, we're gonna stick to. All right. Okay, so now we're gonna move into chapter 6. So let's go back here. Okay, so this morning I added some more stuff over here. I decided for chapter 6, I'm only going to talk about the basic of the file system for now, and then move the next 2 sections, the crash resiliency and directory of naming, move to after 7. Okay, because chapter 7, you need the material as early as possible. So what I'm going to do is I'm going to talk about chapter 6 now, just introduce you what is the actual file system, right? We say we have layers, we have virtual file system, we have actual file system. We're going to talk about what an actual file system look like. Okay, so when you do the virtual file system, you sort of have an idea of what's underneath it. Okay, and after we talk about that, we're going to switch to chapter 7 and talk about virtual memory. Okay, because you need that, for kernel 3. When we're done with virtual memory, we're going to come back and finish, chapter 6. All right. Okay, so again, chapter 6 is not about the virtual file system. It's actually entirely about the actual file system. All right, so so again, we talk about stuff, right? The actual file system maps the inode number to data on disk. Okay, so that's the lower level stuff. Okay, so this is sort of the mapping. All right, so things need to go on the disk, right? Because eventually, when you write to the file, you want the data to stay there, so they have to they can't stay in memory. They have to go onto the disk, and we're going to make sure that the disk access is very, very fast. If you have a slow, file system, the user can really feel it. So it's crucial to have a good performance, file system. Okay. So the requirement, is that it needs to be quick. It needs to be easy to use the file system, and we have a very simple interface, right? Open, read, and write. But since you saw what needs to go on in the open system call, right? It needs to open up many inodes in order for you to eventually figure out the actual inode of the file that you're looking for. Okay, so that needs to be done in a very efficient way. So how do you do that in a very efficient way, right? So that's what we are covering in this particular chapter. All right, and file system is a very important in many different applications, right? Everything sort of needs the file system. Okay, so any kind of software needs it, word processing, browsing, web serving, and stuff like that. So here's one weird thing that actually also requires the file system. Okay, so the operating system also needs the file system. Okay, over here, they sort of describe the paging system. Okay, so remember when we talk about, the address space, well, we saw some address space description, there's a linked list of, I guess we call it what, this AS regions. Okay, and AS regions, sometimes, there's a file object that points to some file. Okay, so the file, the file system needs this. And also, some of these, some of these AS regions, they will point to anonymous objects, right? So these are the anonymous object, okay? And remember that the anonymous objects are the one that starts with a page of 0, okay? And then you start modifying. So they are used to implement BSS, the heap, and also the stack, of your user process, okay? So what happens is that if you need to swap out this entire process, you need to put the entire process to sleep, then basically all these data blocks that were sitting around in memory for this process, well, you want all these data blocks to go to disk. Okay? So therefore, this guy, right, so things that have a file object that point to them, when, and let's say this is a text segment, when this data that are associated with the file segment, that are associated with the text segment, when it needs to go to disk, well, you don't really have to do anything, right? Because that's a read-only segment. All you have to remember is where it came from on that particular disk. Okay, so you don't really have to allocate additional space for the text segment, right? Later on, when you try to revive this particular process, well, you just go to the disk and read the data and then put it in memory, and then voila, you can execute program, you can execute code, for this user process. Okay, but what about the data segment, so the BSS segment, the heap, and the stack segment? Okay, so those data, they have no place to go on the disk. Okay, so therefore, when you try to, swap out this entire process, you need to allocate space inside your file system to store. So over here, this is a disk. Okay, so this is, data can come from over here, but they don't need to go back onto the disk. Okay, but things like the anonymous objects over here, you actually need to allocate space on the disk, so when the process gets swapped out, then they can actually go on the disk. Okay? And later on, when the process is revived, you will bring them from the disk and recreate these objects, and then reconnect everything over here, so you can continue to execute this this process and use the BSS segment, use the heap, and also use the stack. Right? So this falls also within the paging system, because this one will go to the disk. Well, it doesn't really have to be the case where the entire process is swapped out. It could be that you have a system, you're running a lot of processes. So sometimes, things that are not really popular, they get swapped out to disk. Okay, so for example, here is the heap area. Okay, so for some reason, your program, when it's running, it's using the data segment, it's using the stack, and it's not using much of the heap. Is that possible? Of course, right? If you write code, if you don't have a linked list, you never have this heap. So even though you might have some heap objects over here, if this one is not being used by this process, well, maybe you want to have it go into the disk. Okay? So in the paging system, if there are unpopular pages, maybe you have them go to sleep, have them go to the disk, and then over here, you're going to have kernel data structure to remember that, this particular object is really not in memory. So therefore, if for some reason this process starting to access the heap again, then you have to bring it from the disk and, for this guy to continue to execute. Okay, so in that case, this particular process, when it tries to access a memory location that corresponding to this anonymous object, you will get a page fault. Okay, when you get a page fault, you trap into the operating system. The operating system is going to look at this data structure and says, that object is sleeping on the disk. I'm going to bring it in. And then eventually when the object is brought in, then I will restart that memory reference for the user process. Okay, so surprisingly, the operating system also require the file system in order for it to work in an efficient manner. All right, so everything needs the file system. All right, the file system. As we saw before, when you try to open a file, you need to go through many directories. Okay, so therefore directory access needs to be very efficient. Okay, so the directory you got to name things conveniently. So we use the full path name. That's pretty convenient. Okay. But then when it's very convenient, then the lookup is going to be slow, right? Because we have to go through many levels. So these two things are kind of like a trade-off. Okay, so but in the actual implementation, we sort of want the best of both worlds. We want it to be convenient and we want it to be fast. All right, so we're going to see some tricks that the file system will use to try to make these operations efficient. All right. File access, sequential. So again, inside the implementation of the system, there's a lot of trade-off. So if you want to access the file in different ways, and you can only choose sort of a data structure to represent the file system. Should you choose the the data structure so that it's fast for sequential access, or if it's fast for random access? Okay, but since most accesses are sequential, so therefore, if you want to choose an implementation for your file system, you will try to make sure that your file system is fast for sequential access. All right, when you make that particular decision, what's going to, the implication is that random access might be slow. Okay, so you're optimizing the file system for sequential access because it's the most common one. All right, is it possible for you to, to implement a file system so that it is optimized for random access? Of course, okay, but usually that's not a general purpose operating system. Okay, in general purpose operating system, we optimize for sequential access. All right, so as we're going to look through chapter 6, we're going to see most of the time we're going to assume that this is where the access are coming from, and that's why we're going to structure the file system in a certain way to optimize for sequential access. All right. And if it turns out your system, your software is a database system, they're access the disk in a random fashion, then your file system is not going to perform very well. All right. Okay, so section 6.1 talks about the system 5 file system, right? S5FS. Okay, so we're going to talk about the actual file system that implement this this file system. Okay, the system 5 file system is very important because it is the ancestor of many of the current file system. Okay, from system 5 file system, the next one is called the fast file system. Okay, from the fast file system comes the ext2, and then from ext2 it comes ext3 and the ext4. Some of the stuff over here. Okay, and I think on the Solaris machine, they also have their file system starting from the fast file system. All right, so we're going to look at this file system that was built in the 80s, so it's a really old system. But some of the new one, they use the good ideas from the old system. So the current system, actually looks somewhat like the system 5 file system. Okay, so we're going to see what it looks like, and we're going to see how does the data get placed on disk, and how does that affect the file system performances. And then we're going to see the improvement of system file system, particularly how do you, when it go from system file system to the fast file system, what kind of improvement was made, okay, and what kind of performance gain that we have by making these, these sort of operating system adjustments. Okay, so it turns out that if you make the right kind of decision in the operating system, you can go from one file system to another, and you can actually perform, much, much better. Okay, thousands of times, better than the previous implementation. Okay, so it turns out that the software does play a big role in, improving the performance of the system. Right? Some people think, oh, you just get faster hardware, and then every problem will disappear. Turns out that's really not the case. Okay, operating system, does make a big difference. All right. So the system file system is a very simple system. It's kind of slow. Okay. And also one of the big problems is that it's not very tolerant to crashes. If you have an operating system crash, chances are your file system is messed up. Then you sort of have to rebuild the file system or somehow fix it. Okay. It's reasonably efficient in using space. Okay, when we talk about space, right? I think when we mention memory allocation, we talk about internal fragmentation. We talk about external fragmentation. Right? Fragmentation are no good because you're going to end up with wasted space. Okay, so similar kind of allocation can also be done on the disk. Okay, so and the disk has internal fragmentation and external fragmentation. So therefore, you're going to end up with wasted space on the disk. Okay, so over here it says, well, the space usage for the system file system is actually fairly efficient. Okay, although it doesn't really have compression. With compression, you can actually save additional disk space. All right, so we're going to look at so what is the file system? Right, the file system, it's about these on-disk data structure. You're going to have data structure, but they are they are layered on top of the disk. Okay. And when you try to access the data structure, you actually have to go to the disk and then get the data structure from the disk. Okay, so for example, we saw the directory already, right? The directory is the data structure. It's a list of, key value mappings, right? Those who knows, Java, right? It's a map data structure, sitting on the disk. Okay, so that kind of data structure, when we need to retrieve, either the entire data structure or part of the data structure, we need to issue commands to the disk to bring those data in. Okay, so that can be very, very slow because disk is a very slow device. So it actually matters where you place these data on the disk. Okay, if you put these data structure on the disk in the wrong place, then when you try to retrieve them, it may take you a very long time. But if you organize them just right, all of a sudden bringing those data structure into memory can be a very fast operation. All right, so we're going to see these kind of stuff. All right, so these data structure represent, what do they represent? Right, they represent inodes. Okay, they also represent the free space. Right, so if you look at the disk, right, this is the 500 gigabyte disk, right? Okay, it's like the one on your laptop, right? Most of it is empty. Okay, so therefore, so there are parts that are being used all over the place, right? And then there are parts that are completely empty. Okay, so looks funny. So all these empty space are your free space. Okay, so part of the file system is to manage these free space, right? Why do you want to manage this free space? It's just like memory allocation, right? When you say, I want to call malloc, I want to allocate free space to be used, in this case for a file, I want that operation to be done very quickly. Okay? If it takes a long time for you to find a free block on the disk so that you can use it in a file, then the performance is going to be really bad. Okay? So you want to manage the allocated space. In this case, they're occupied by file, directories, special files, all these kind of stuff. And you also have to manage free space efficiently. All right? So we're going to see how this is done in the System 5 file system. And by the way, System 5 file system is, S5FS is one of the kernel project, that we're skipping, right? The fourth assignment in the original Unix operating system is called S5FS. So when you implement kernel 3, you're going to turn S5FS equal to 1 in config.s. So all these code are provided for you. All right, so kernel 1 and 2, I guess 1 and 2, you don't need F5FS. But when you do kernel 3, you're going to set this one, and it's going to use the lib s5fs.a inside the kernel directory, and that will have the System 5 implementation. All right, and unfortunately, you don't get to see the code because, again, this assignment is used by other universities, so we can't give you the code, just like the driver's assignment. Okay, so what does the system file disk look like? Okay, so if you have a file system that's in the System 5 file system format, okay, then this is what a disk looks like. Okay, so remember, every disk or every disk partition, you can say, I want to install a file system onto this file, into this partition. On Windows, right, there's FAT16, FAT32, the NT file system, etc. On Unix, these days, you do ext2, ext3, ext4, right? So every disk partition, you can potentially install a different, file system. Okay? So this is one disk partition. Okay? And if you have the System 5 file system installed on it, then it looks like the following. Okay, so over here, this is sort of a linear view of this file system as a 1D array of disk blocks. Okay, it's a one-dimensional array. It's just an array. Okay, so the disk is organized in an array. Okay, and it's an array of blocks. Okay, so every block is just a number. Right, tell you which block it is. Start from block 0, 1, 2, all the way to the number of blocks minus 1. All right, so that's what the disk looks like. It's just an array of blocks. Okay. The first two blocks have special names. Right? The first block is called the boot block, and we've seen it already, right? We see the the bootloaders is inside the boot block and stuff like that. There's a magic number and there's partition table, etc. The next block is called the super block. Okay, and then comes a region of over here is called the I-list. Okay, it's a list of inodes. Okay, so this is an inode list. Okay, so again, the inode is just an array of inodes. Okay, and an inode is a data structure on disk. Okay, so this is just an array of data structure on disk. All right, and then followed by the data region. The data region again is just an array of blocks, disk blocks. Okay, so over here again, there these data blocks. All right, so that's what the disk looks like. Okay, very simple data structure. Okay, just an array of blocks. All right, so let's look at a little more detail and see what's inside the super block and what's inside the IList. The data region is, we don't need to describe it because they're just blocks. Okay, so if you allocate, a particular, so let's say that you want to create a directory. Okay, how do you create a directory? Right? If you want to create a directory, you're going to get an inode. You're going to get an inode from the IList. Okay, and then this directory needs data to be stored in that inode. Right, so the data for a particular inode is that table that says I want to map dot to some inode number, map dot dot into some inode number. Right, when we create an empty directory, that's all we have. Okay, so clearly this is a very small data structure, so it's going to fit into one block inside the data region. Okay, so therefore this particular directory will need a pointer from the inode to the data region to say that this file contains one disk block. Okay, and this inode inside the IList will contain information about how many bytes are in this file and where is it, and other information. All right, we're going to look at this detail pretty soon. But over here, you just you can see that the stuff in the inode, they just point to these blocks in the data region. Okay, and in the data region, do they point to each other? Right? If I have a regular file, like a GIF file or a PNG file or something like that, right? If this is one of the data blocks, then it just contains the raw data bytes. So the raw data bytes are interpreted by the application that knows how to deal with these files. Okay? But if it's a directory, then inside this data block, right? If you open this, file, in the data region, then it's going to look like this. Okay? So inside this, the raw data is going to be, the key and the value mapping. So you can actually interpret the value mapping over here as an inode number, right? An inode number is going to give you an index into the IList. So you find another inode, open this inode, and then this one will point you to this block on the disk, and then you keep doing this recursively. All right. So this is all you need, right? You have a what is the super block doing there, right? But all you need are the IList and also the data region. Okay, array of inode and array of data blocks. Okay, so super block is where you keep track of, the rest of the disk. All right, the super block describes the layout of the rest of the file system. Okay, so it tells you, where the root is, right? Because once you find the root, you can find the entire, file system because the file system is a hierarchy, right? If it's a hierarchy, all you need is the root. You don't need anything else. Okay, so therefore, you can start from the super block, and that will lead you to, everywhere else. Okay, it also contains the heads of the free list. All right, so most of the block in the data region, they are free, right? They are not. So if the block is not free, what does that mean? Right, that means that it belongs to, it belongs to a file, it belongs to a directory, it belongs to a device, or it belongs to something. Okay, if it doesn't belong to anything, that means that it's free. Okay, so all the free blocks in the data region, they need to be maintained on a list. Okay, so in the system file system, right, they use actually a list implementation, a linked list implementation for all these disk blocks that are free. Okay, so if you have a block that are free, it sits on the free list. Okay, if you are a block that's being used, where does that block belong to? How do you find that block? All right, if a block is free, then it belongs to the free list. It's in the linked list. If the block is used, where does it belong to? Well, it belongs to, if you start from the root, you should be able to find it, right? It might take you forever to find it, but you should be able to find it somewhere, right? It will be reachable from the root node. Okay, unless you have a broken file system, yeah, then you're gonna have, if you have a broken file system, right, you have a tree, and then you have this part of the tree that's not reachable from the root. Okay, I mean, if you have a bug in your implementation, you might end up with something like this. But otherwise, every disk block that are allocated, you should be able to reach it from the root. Okay, you might not know how to get there, okay, but you're convinced that there's a way to get to it. All right, thank you. Okay, the IList is an array of inodes, and every node represents a file, right? And a directory is a file, a device is a file, etc. Okay, so this is what inside of inode look like. Okay, inode is on this data structure, right? So it's a fixed size data structure. Okay, so this is a fixed size. Okay, it has several fields in here. Number one, this is the device that it's on. Okay, why do you need to know what device it's on? Right, because the device tell you which device driver to use in order for you to look for data on for this particular file. Okay, so again, device, right? It's a major device number followed by a minor device number. Major device number tell you which device driver is to contact, and the minor device driver tell you where to go. Which device managed by that device driver, and that's where the data is stored. Okay, so this one is that information stored over here. Okay, it's also the inode is self-contained, right? So every inode knows its inode number. Okay, so over here the inode number is also represented over here. Okay, and the third field over here is what type of node this is. Is this a regular file? Is this a special file? Is this a directory? So when you open up an inode, it's self-identified to be a regular file or a directory node or a special file. All right, so it's stored right there. And then the link count is how many references do you have into this particular file. So if the reference count equal to 0, that means that you can actually delete this inode. Nobody needs this inode anymore. Okay, and then the next one is the ownership. Okay, the owner group ID and the the group owner group ID is stored over here, and I think each one of them is 16 bits long. Okay, so this is a 32-bit quantity that's stored right here. Okay, next one is the size of this file. Okay, if it's a directory, it also have a size. If a regular file has a size, device, then it's just 2 numbers, right? It's easier. And then the next part is the disk map. Okay, so this map are pointers to the data region. Okay, so what is the disk map? Okay, so the disk, right, I drew this picture that there are pointers to point here. Okay, so that pointer point from the disk map area of the inode. Okay, so over here, this is the pointer, contains a lot of pointers. Some of them are 1 level of indirection. Some of them are 2 level of indirection. Some of them are 3 levels of indirection. So they can point to all these disk blocks. Okay, I'm going to start looking at some of this stuff, what it looks like. Okay, so in this case, the disk map is a fixed size data structure, right? So how does a fixed size data structure point to something that's a large file? Okay, so again, you got to use the indirection. Okay, so the disk map for system file system has 13 locations. Okay, so you can store 13 integers. Every one is going to be a block number that reference the data region. Okay, so all these things are block numbers. Okay, but the way you interpret this, I got 1 minute, right? Is that the first 10 of them are direct pointers. Okay, so pointer again, they just contain a number which is the block number on disk. Okay, so the first 10 is direct. Okay, the next one is single indirect. Okay, and then pointer number 12, or in this case index number 11, is double indirect. Okay, and the third one is triple indirect. All right, so I'm gonna pause stop right here, and next time we're gonna see exactly what all these means. All right.